First of all, good evening to everybody. I'll start off by asking, who knows Apache Spark at all? OK, that's good. Majority of the audience. This will be basically the most basic terms of Apache Spark, some things about the infrastructure. Because most of the audience actually knows Spark, you can interrupt me, be Israeli, and actually ask about what interests you, because I can stand here and talk about Spark like for 4 days. And if I speak too fast, just raise your hand, wave, or do something like it, because I want it to be understandable. So, Apache Spark 101. My name is Demi, as already introduced. I'm the VP R&D currently of Panorays. I'll give a brief slide about the company and everything, but this is out of context of the basics of Spark. So a bit of introduction about myself and the background for you to be able to understand where I come from and to ask the relevant questions. If I know it, I will stop and answer. If I don't, I still will stop, answer with confidence, and lie. OK, so I'm also a Google developer expert. That basically means that Google says that I talk a lot. I organize a couple of developer communities. One of them is Big Things, focused in big data, data science, and DevOps, and also Google Developer Group of Cloud. It's not mainly focused on Google technologies. It's focused in cloud technologies in general, and the OFAC Alumni Association, which is the unit that I was in the Air Force. In the past, I was a senior data engineer at Windward, and the Air Force, I was like for 8 years, software engineer and a team leader in a missile defense system. So this is the basic concept. What do we do at Panorays right now? We're a startup company, and we do automation of cybersecurity management of third parties. How many of you know what third parties are? Suppliers, vendors. Probably you're using most of them as software developers. Again, another question. How many of you are software engineers in the manner of developing applications, etc.? OK, how many of you are infrastructure guys? More on the operations side? Less. OK, awesome. So I just wanted to know the division of the audience. Basically, what we do is, you know, the source control, cloud service providers, maybe CRMs and ERPs. These are like the IT vendors that you're using. And you can see other type of vendors, which are like law firms, accounting companies, and even flower delivery companies that you're using. All of them are vendors. And more than 60% of all hacks today are not made to the enterprises and to big companies. They're made through the supply chain. And basically, we're helping organizations to manage the cybersecurity risk imposed by their third parties. So this is the context of Panorays. We're doing everything without installing anything in the evaluator side or in the supplier side. We're doing everything in the hacker's point of view. So we basically took the behavior of the hacker and dismantle it to small behaviors, and then we collect all of that data and then aggregate everything and create the attack surface of the organization. This is the high overview of what we're doing. So to start off speaking about Apache Spark, we'll start off speaking with another buzzword, which is big data. How many of you have heard about big data? OK. Awesome. So let's define big data, OK? Because it's really subjective of who's talking about big data and what do we speak as big data. There are like many V models, the 7V model, the 5V model, but we'll focus on the 3V model that defines big data. First of all, the volume. How much data do you have? I'll ask that question, another big question. How many of you really know how much data do you have in your company? An estimate, OK? And this is the funny thing. This is really important when you're tackling some kind of problem in the matter of data at all. How much data do you have? Because if you have the capacity of 100 gigabytes or a couple of tens of terabytes or hundreds of terabytes, the solutions are totally different from each other. So basically, you need to define that. This is one of the hardest questions. Every company or person that I talk to, and I ask him how much data do you have, the first answer he gives me is?
A lot.
A lot. Awesome. And when I ask, okay, how much is a lot? The answer is?
I don't know.
No, it's not I know. I don't know would be a good answer. Really a lot, okay? And you need some kind of estimate at least about the capacity of data that you have. The other one is velocity. How fast is the data coming? Okay, this is really, really important. How fast and the frequency also. Because again, if you have a really big workload coming once a day, comes one solution, and the other way around might be in small chunks during the whole period time of the day. And of course, one of the biggest changes in I think the last 30 years is the variety of types of data. Because let's say if you're working with sensors, usually people used to work with predefined APIs, some kind of message structure, binary message structure that you would need to parse and then save the data, and sometimes even not saving the data. But nowadays you have JSON formats, you have maybe RPCs, some kind of API that you're working with, I don't know, it varies. And all of that data needs to be digested and inputted into some kind of database. And because of that, we have the problem of variety. If you've defined your problem as all three of these characteristics, then basically you have some kind of big data problem. So some strategies and terms that you need to know before we actually start tackling big data solutions. Everything starts to be distributed. If you had, in the past, a really big server that does all of the digest and saves all of the data, basically right now you have the notion of nodes. Okay, you're distributing everything, you're distributing the data and the workload among a lot of nodes, and you're doing a lot of replication. Okay, in the contrary of actually backupping everything. People used to have a big database server, back up everything, and then if something crashes, something happens, you just come up from the backup. How many of you have managed in the past to come up from backups? It's rare, okay? It's really rare. So all of the big data technologies, the distributed technologies, are using replication mechanisms to actually hold all of the backups. And if something fails, we have replication of the data. We're using methods of relaxing consistency requirements. Something will be eventually consistent. Relaxing schema, again, working with JSON formats and things that are more flexible. And also optimizing the data to fit our needs. This is the really important thing, in the contrary of actually putting everything inside the database and then I will let the database do the heavy lifting. Here, I take the data, restructure it according to the queries that I will need to do in the future, and then actually do that according to the data. And duplicating the data is not a bad word, which in the past, when you normalize everything, it was a bad thing to do. Okay, how many of you know NoSQL? Awesome. What is NoSQL?
You no longer work with stabilized schemas with normalization and the constrained structures.
Okay, awesome. This is correct. But let's say the term says not only SQL, okay? And the really important thing that is things are starting to be distributed across a lot of places, and the pinpointed data is denormalized most of the times, okay? I won't go into depth in all of the ACID things, but the thing that you need to know that everything in the matter of relational data comes with high costs. Also with the pre-assumptions that you have on the data, and you usually lose a lot of flexibility there. And you need to rescan all of the data, you need to denormalize the data in memory, etc. So this all comes with nice things as developers, but in the matter of scale, it's really, really hard to start managing all of these things. So this thing you need to keep in mind. Let's take the NoSQL landscape, okay, and which kind of data sources we're starting to work with. So we have graph databases. Have you heard of them? Have you heard of any? Yeah, I will show some examples in the next slide. Key value stores, okay, which actually are the basic things of NoSQL. Document stores like MongoDB or OrientDB. And Y-column stores that we'll see examples. And this brings us to the CAP theorem. How many of you have heard of the CAP theorem? Okay, awesome. Consistency, availability, and partition tolerance. And this is how it looks. Basically, what they say that you need to pick two. Okay, you can't have all of the great things in the world. Google says that with Cloud Spanner, they've solved the CAP theorem problem. I won't say it's not true. They did something really amazing, but still. And you will see a bunch of databases in the groups of actually two. When you want a database that is highly available and also consistent, then you go to the whole part of relational data. When you want to go in the matter of availability and partition tolerance, you have Cassandra, DynamoDB, Raya, CouchDB, etc. And you will say that Cassandra is a semi there. Why? Because they say that it's tunable consistent. You can actually do a query in Cassandra that waits for all of the answers and all of the nodes to replicate, but it fails like almost 100% of times because of timeouts. So you can do that, but it doesn't always work.
Can you say a word about consistency and partition tolerance?
Yes. So here, I still haven't finished. And all of these databases are not highly available by default, okay, but they are partition tolerant. If something happens to the data, you have replication, etc. And they're consistent because when you like commit some kind of record, it is updated. And that's it. Because of like MongoDB, you can say that it has a single master architecture in which you write only to the master. So what you had written and you got acknowledgement, it's there. Okay?
And what about the Redis?
Again, it's the same key value store. When you update something in Redis,
It's only on memory, right?
not only. You can have it like doing incremental backups and everything, and then like rise from something that happened. But still, it's mostly for the use case of putting things in memory and doing things super fast. Okay, again, it's not the focus of Spark, but I wanted to show you the landscape of actually the data sources that we're handling when we're working with big data workloads. So, I just want to keep tabs on time. When did we start? Okay, sababa. How many of you know Hadoop? The Hadoop ecosystem. Awesome. Again, it's an ecosystem. It's not a framework. And all of the things that Hadoop was based upon were flexibility, scalability, low cost of servers and infrastructure, and fault tolerance. Everything there was based on these principles. Okay? And from that, all of the things that came after, also Spark and everything, are based on these two. And the core components that all of the Hadoop infrastructure was based upon was HDFS, which is the Hadoop file system that was based on the GFS, the Google file system. Everything like came out as a white paper in the beginning, and then afterwards they implemented open source frameworks on top of it. And the MapReduce. This is like a notion of programming. How many of you know functional programming? Okay, even if you're using Python, etc., all of these like terms are really, really common there too. And in the version 2 of Hadoop, we had Yarn, yet another resource negotiator. In the first version of Hadoop, what we had is a cluster of machines that ran all of that infrastructure. Once we had some kind of job that wanted to do some kind of workload or compute on top of that, it basically got all of the resources. And that's it. Nobody else could run. So because it's not efficient, then we created, or they created Yarn, which I go to somebody, the resource manager. I ask the capacity of some resources. I get it, if it has something available, and then I start running my job. So I can run multiple jobs in parallel, maybe something out of like Hive, and a Spark job, and maybe a raw MapReduce job as well. So keep calm and MapReduce. And this is basically how the hello world of big data works and looks in the manner of MapReduce. This is the word count. We have multiple files that we first map it to ones. Then we aggregate all of the ones into one machine, and then reduce until we get the word count in the distributed file ecosystem. This is how it looks. We have the mappers. We have something that splits all of the data. We have the notion of shuffling that we'll talk about briefly in the next slides. And then afterwards, we have the reduce phase that aggregates everything into the relevant pieces of data that we need to keep. OK, this is how the Hadoop ecosystem looks like. OK, we have the Hadoop core, which holds Hadoop common. Everything, by the way, is written in Java. OK, so don't be surprised. The Hadoop common are Java libraries. The HDFS are processes that run on top of all of this. And MapReduce and Yarn work in conjunction with the HDFS as a data source. On top of it, people created higher level applications for convenience. So we have Hive, Pig, query languages, ETL languages, databases that sit on top, Uzi, which is like a scheduler on top of Hadoop, and Zookeeper, Scoop, etc. And the new kid on the block, it came out as an open source in 2013, which is Spark. How many of you are working on cloud environments? Google, Azure, AWS, awesome. How many of you are working on-prem? Fun, right? No. I know. And for that, of course, some big companies identified the problem of working in this kind of ecosystem with a lot of tools, because everything is complicates all of the workloads more and more. So they went off and created production-grade distributions that hold all of the ecosystem that we showed in the previous slide in one package. So Cloudera, MapR, Hortonworks are the most common deployable on-prem and also in the cloud packages. And of course, we have our cloud vendors, so they actually created platforms to hold all of that infrastructure in one piece as well. So Amazon has Elastic MapReduce, Google has Dataproc, Azure has its own managed Spark and Hadoop. I think it's called HD Insights. And also other kind of companies like DataStax, which incorporates Cassandra, has a distribution with Cassandra and Spark because they work together as a distributed data store and distributed compute framework. So, summary of Hadoop: large volumes of data that we need to store and process, semi-structured data or unstructured data. It's not categorized well. Maybe it's, I need some complex batch jobs that run simultaneously to some other workloads that I have. And basically, when you don't know what you're going to do with the data. Okay, you want to save logs just to analyze them afterwards, and you really don't know right now. And because storage is cheap today, then let's store everything and then analyze. Yes, Oli?
In which cases you won't choose Hadoop?
In which cases I won't choose Hadoop? If everything can be and can fit one big large server, drop the complexity of actually handling a distributed system and put in the effort in one server that will run that.
So the size of data.
Yes, and if you know that the size of your data won't grow, okay? I will talk a bit about the separation of the distributed data store and the distributed compute framework, because all of these packages are really reliant on the HDFS underneath. And what happens if you have, let's say, 100 terabytes of data, but this is all of the data that we'll have ever. But you want to scale your compute. You need to add more nodes, but you don't need that in the manner of storage, right? So you need to add compute nodes, but they're combined. And if you separate them and put in not HDFS, let's say an object storage, Amazon's S3 or Google storage, then the data is scalable infinitely, at least that's what they say, and you ramp up the relevant compute that you need according to the workload that you want. Tomorrow, you don't need 100 servers, you need only 50. Kill 50 servers and that's it. You don't need to, if you would kill 50 nodes on HDFS, it will be really, really painful. Okay, everything will start the replication phase, and again, you might lose data even if you don't have the relevant replication. Okay?
So the question was when we need to use big data technology?
Distributed framework of some kind. Yes, yes. Hadoop, Spark, other kind of distributed. Yeah. You can take Cassandra for an example. It's not something in the Hadoop ecosystem at all. It's a distributed database. If you don't need that like high write throughput and complexity, don't use that. MySQL works fine. Postgres works fine, really. In really high scales as well. Yes?
If you need to process the data in streaming mode, so I guess Hadoop won't work as well. It has large latencies compared to...
Yes and no. It really depends on your workload. The guys from Forer can tell you a lot about like streaming and working with Storm. You're still working with Storm, right? Yeah. Okay. You have different kind of solutions for that. And we'll talk a bit about like Spark streaming and why it's not exactly streaming. We'll get to that, and if you have other questions, just ask me through the lecture. So, what is Spark? Okay, again, it's another buzzword that people like to use. It's a general-purpose cluster compute framework, and you need to take that into account. It's not a database, okay? People ask me a lot of times, okay, I want to query Spark. It says nothing. Okay, you can't query Spark. You can't query with Spark. It's a running infrastructure of distributed compute workloads. And everybody says, okay, it's really, really fast because it does everything in memory. It's not exact as well, because it does in memory or on disk. It really depends on you as developers, on what you define for the workload to run, actually. And Spark has low-level APIs that you can work with the bits and bytes and work with RDDs, or you can work with high-level frameworks like Spark SQL, machine learning, and add more things from Spark packages that I will show in the next slides. So basically, the philosophy of Spark was to simplify things of distributed compute and give everything for people like from the academia to work as analysts on top of like pretty convenient and easy to use frameworks. Like powerful domain-specific languages that I can define in human spoken language things and just run them across multiple nodes on very large volumes of data. And predictable releases. This is really, really important, okay? And they're keeping tabs really well on that. Stable release every 3 months, and a really large ecosystem of developers that are actually developing that. All of the big enterprises recognize Spark as something that helps other people, helps them, so they are contributing a lot of code to it as well. And you can see like really big companies, Yahoo, eBay, IBM, Amazon, everybody is contributing to Spark because they want to adjust Spark also to their tools. And because of that, they find bugs, of course. So how many of you know OpenHub? OK, this is a great website. If you're using open source packages, you can actually see the summary and the dashboard of the activity of a library that you're using. I won't say that it has everything, but it has a lot of things. And for me, like even as an engineering manager, as a software developer, if I want to use something, I can see the activity not only on GitHub or by the contribution, by the community, the division between code and comments, and how much like activity it had in the past years, and looking at history as well. It's really important to see if I really want to use some kind of library. So you can see the development of Spark from like 2013. It just like, I don't know, it went up to like 2 million lines of code. And you can see the big chunk of code here.
Like in 2012, they just removed all of their code.
Yes, because this is a project that actually, I'm not sure, I think it's biased a bit, but it started from the academia. Spark, in general, started as like a pet project to see if Mesos as a scheduler works. Matei Zachariah, the guy that started, the CDO of Databricks, he actually started from writing Mesos. He created Mesos and then said, okay, I need some kind of use case to actually show that distributed like scheduler works. Oh, let's create a compute framework that works on top of it. And then like this is what happened to Spark, and Mesos is still there, let's say. So the Apache Spark project was founded at UC Berkeley, and the main contributor is a company called Databricks, which supports and actually creates also a managed platform of Spark. We have interactive shell in Scala and Python, which is Spark Shell and PySpark, and currently in the stable version of 2.2.1. I will just drop the slide. You can see a comparison of running Spark and running regular HDFS on regular data centers. But what's the bottom line? What's Spark and what is the main benefit of using the framework is basically a unified tooling platform. Okay, in Hadoop, we had a lot of batch operations and some kind of databases like Edgebase that worked on the operational side. But here, in one framework, we get all the best of all of the worlds. We get also batch analytics and batch scripts that we can run in the single framework, in the same language, and the same domain-specific language as well. We have streaming framework. It's micro-batching more, but still. And we have an interactive shell that data scientists and maybe even for developers to explore in one ecosystem. So this, in the manner of infrastructure and like schema, this is how it looks. We have the Spark core libraries that work with RDDs that we'll talk about what RDDs are. We have data frames and data sets, which are the notion of actual tables on the unstructured data that we're creating. And on top of it, we have a lot of higher level infrastructure frameworks. Spark SQL actually translates and has a catalyzer that translates SQL queries to MapReduce operations on top of data frames and also on RDDs. We have a graph analytics framework. We have MLlib, a machine learning library that Avi will talk about a bit, right? And we have Spark Streaming, Spark R, they created a porting for R, and also Spark packages, which is really, really important. Why do I say that? Because most of the connectors that you have as developers to different kind of databases, data sources, and maybe even tutorials, and also like other additivities that people want to contribute to the open source ecosystem and don't get it into Spark, you can open up your own GitHub and create your own package. Let's say even DataStax to create the Cassandra connector. They put in a GitHub project inside Spark packages and you use it as users as well. Okay? Any questions about this, by the way? Because it's a really high overview slide. Okay, awesome. Spark languages. So we said it should be convenient to other developers, right? So it started off written in Scala because most of the notion of working with Spark is with functional programming. So because the notion of mapping things and filtering, etc., Scala was like the really elegant language to write it on. And of course, because Scala is a JVM language, all of the reuse of code, of infrastructure, etc., was with Java. So the first APIs that they actually created were in Scala and Java. Afterwards, of course, Python is the, let's say, most common language of data scientists nowadays. So they wanted to, for people in the academia that know a bit of programming, to actually go into depth in the ecosystem. So they created an API in Python, which was pretty different in the beginning. When I started using Spark in 1.0, I think, it was pretty different. Okay, it worked differently, and the interpreter worked differently, but they started like evening up the APIs, and today I think the Python API is almost like similar to, almost 100% identical to the Scala API, and in R I really don't know because I've never used Spark R. Let's talk a bit about the architecture and how it actually runs in a manner of runtime. So we have the JVM, which all of the nodes have some kind of Java version, of course, and we have the Scala runtime running on top of the JVM. On top of it, we have the DSL and the API of Spark. How many of you know what a REPL is? Okay, read, evaluate, print, loop. Okay, the same that you have in JavaScript, the same that you have in Python. You have that in Spark, in both PySpark and Spark Shell. And of course, the runtime says nothing if you don't have data to actually process, so it needs to connect to some kind of distributed data source. It doesn't have to be distributed, but it better be, because if not, you're starting to work with some kind of bottleneck, which might be like a MongoDB database or whatever. And of course, it does all of the integration to HDFS naturally. And you have some kind of cluster manager to actually ask resources out of, because I want to run some kind of job, some kind of workload compute on top of a cluster, right? So it has some kind of cluster manager. Yarn and Mesos are two examples of that. I heard today even implementations of running Spark on top of Kubernetes, which is pretty awesome. And Spark, out of the box, comes up with its own cluster manager, which you can share resources. Okay, you just launch some kind of workload of only Spark, and only Spark can run on top of it. And of course, the Scala REPL is running on top of a Scala compiler. Spark is kind of like a DSL on top of the cluster management. Okay, so we have if you look at it, it's basically some kind of distributed collections on some kind of cluster. So you have maps and lists on top of a cluster of servers. And on top of it, of course, you can run some kind of functions, mapping functions, flat map, filtering, reduction, folding, etc. You can see a similarity to the collections API in Scala, the functional collections API. Okay, I won't show you the example. You can see it on YouTube. It's something that I recorded, I think, in 2014. But everything is basically using the bare bones of Apache Spark, which are resilient distributed data sets. And these are basically, as I said, collections in memory or on disk that are distributed across multiple nodes, logical nodes or physical nodes. And they are all fault tolerant. They are really, really similar to lists and arrays abstraction. A really important thing that you need to know, a term which is called a DAG, a directed acyclic graph. And this is how the execution plan of Apache Spark jobs are planned. You basically put in some kind of blueprint. This is the code that will run the workload. And then it takes this code and translates it to some kind of directed acyclic graph that will run all of these like workloads.
So basically, you can't really create loops in your computation.
No, no. But you can create something that comes like continuous ones, like micro batches, etc. Yes?
So the way that data is actually saved depends on the functions that you define that you want to run in advance?
Yes, and it depends on the manner of partitioning. Okay, how you partition your data during your compute. Because let's say when I create the schema, the blueprint of running a Spark job, I can define, okay, I read some kind of data source. Let's say it was from a single data source in a single partition, just to simplify things. And then I want to distribute that across like 10 different machines. So I repartition the data and divide it into chunks of like a tenth of pieces, like a tenth of the data will be in each node. This is repartitioning. And then it's distributed across the 10 nodes, right? Then when I save the data, it is saved in 10 different partitions. Because it is being saved on HDFS, a distributed data store with 10 different like machines of compute that write the data.
And also because you want to go through everything. You have that function that goes
You might want to go through everything. You don't have to.
Yeah.
It's up to you as a developer. Okay? And the most important thing to remember, RDDs are immutable. Okay? And because of that, the paradigm of actually running everything fault-tolerant works. If we didn't have this assumption, nothing would work. And why do I say that it's immutable? Because every transformation that you make on the data, let's say I take a map function and then do filter function and then blah, 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 each phase creates a new RDD.
So you copy the data all the time.
Exactly. But the infrastructure and the whole framework is smarter than that. And we'll talk about like different kind of transformations and what it actually can correlate into like multiple and chain them into multiple like tasks that will run on a single machine without creating a new RDD. Okay, we'll show that in next slides. In the notion of Spark, we have like two things that we can actually do. One of them are transformations, which are lazy evaluated, and this is like basically creating the blueprint and saying what are the steps that I want to do. And what actually triggers the DAG, the actual compute phase, are actions. It might be count, which counts the rows, the amount of rows, and it might be collect, that takes all of the data and ingests it into the driver machine. And we might have reduction, etc. A common mistake that people do when they create their first like Spark job, create some kind of blueprint of mapping, filtering, etc., run the job, and nothing happens. Okay, why didn't anything happen?
Because they are lazy.
They are lazy evaluated, so they didn't put in any action, so nothing happened. It's correct because you didn't define that. So you need to keep in mind that you need to do something. Even in the last phase, do save as file, and it will trigger the DAG like from below. So it will know that I have some action that I need to create, that I need to start the compute. I will take the DAG and start executing all of the things, aggregated like from the back. So how does it look in memory? Okay. So if we take our whole cluster, we have a 4-node cluster, and we have the total RAM of all of these machines.
So each color is a different node?
Each column is a different node.
And each color?
And each color is a new RDD that I'm creating.
Like a new step in your computation?
Steps, yes. And this is a transform, this is a transform. Okay, and I'm creating a new RDD. So maybe I did here some kind of like aggregation phase, and it created 2 new RDDs, 2 new partitions in the new RDD, and then I redistributed everything and did, let's say, like repartition to 4, and then I partitioned it to 4 different partitions.
So it's from different queries, the RDDs are created?
Don't say queries, transformations.
Transformations, yes.
Mm-hmm.
But it's, okay, so it's created per transformation.
Yeah, and it might have been inlined if some criteria had been met. This is the real important thing, and I will talk a bit about it in next slides. So, how does it look in the matter of machines? We have yes.
Well, the previous slide. How can you predict the amount of storage you need for the?
You can't.
Okay.
No, really. Basically, you can't. You need to know your data. Okay.
So you have 10 terabytes of data. So how much of storage are you going to need on each of the nodes?
You need to ask how much, not storage, how much RAM do I need on all of the nodes? Because storage, you might have a different like phase for that. Because not everything has to run in memory. It can take an ingest of a specific amount until it runs out of memory and RAM. And then if you define it memory and disk, then basically it will thrash the disk, put some of the data on disk. After it analyzes that, free some memory of RAM. But again, it takes time. If everything is not in memory, writing to disk is expensive, right? Reading from disk is expensive. I'm trying to avoid that. So you might even want to actually avoid that during your like compute phase and downscale the amount of data that you're running on top and run in slices, because it will run much faster and not like thrash to disk all the time. So this is how like Spark machines look like. We have the notion of the driver. This is basically the main function of your application. Okay, the main function will be running on top of a specific machine. There are some kind of constellations that you can actually run that. And let's say in Yarn, you can run a Yarn cluster, which means the driver will run on some machine in the cluster. And if not, if you run Spark, let's say Yarn client, then basically it will run on the machine that you're running the code out of, the script. So it might be the driver machine, the master machine. It might be your local computer as well. But what happens if you actually close the computer? Then the driver dies. And he is basically the controller of tasks. He takes your DAG, takes all of the smaller tasks that he had created, and starts sending them to the worker machines, which should be homogeneous and be the same. It will be my recommendation to you, because if not, you will run into many other kind of problems. And the executor takes the tasks and moves the task according to where the data is resided at. This is the really important thing. And because of that, the whole notion of distributed computing is not taking the data, let's say I'm sending some kind of query to the database, it does some kind of compute and returns the relevant things. I'm taking the compute and sending it to the data, and there the executor, the worker, takes care of all of the other things. We've talked about transformations, right? So there are 2 different transformations that you need to take in mind, and it's really, really important. Narrow dependencies, okay, are ones that you can actually like inline one after the other. Mapping, filtering, etc. These things can be inlined by the framework without you defining anything. So this is really, really efficient. You won't create new RDDs and you won't spend a lot of data. Wide dependencies are ones that you actually need to move data across nodes. And what happens when you need to move data across nodes? You even don't hit the disk, you hit network. And you create a really big load on the network that the cluster resides upon. And the thing is that wide dependencies are really, really costly in the matter of time. So try as much as possible avoiding wide dependencies, but it's not really possible. What actually Spark gives us as a framework on top of NoSQL data stores is what we used to miss in the matter of NoSQL, which are what we miss in NoSQL databases. Relational, which means
IDs and
okay.
Schema
Relations.
Joins, unions, okay, all of the things that we don't have in NoSQL databases. So if you simplify things, we have data stores which are distributed across a lot of nodes. We can't join them all. So Spark and distributed frameworks, distributed compute frameworks like these gives us the ability to actually do all of these things. Okay, and for that we actually need a lot of memory, a lot of compute power, etc. Okay. So some basic terms. Again, we had narrow dependencies that look like this, filter map, union as well. We just combine everything to new nodes. And we have the group bys, the joins, the really fun thing that we had in relational databases, but in Spark. Spark doing that on top of distributed data stores. So here you can see the listing of all of the possible transformations and actions. You can see that on the Spark website as well. And this is the basics of the infrastructure of Spark. Terms that you need to know. And usually nowadays, nobody uses the RDD API. Unless you need something really, really specific that you need to do something really performant in a matter of, I don't know, optimization or something, when you need to read from a new database that you've created or something, then you will use the RDD API. But most of the people use Spark high-level APIs, which we will talk about. So one of them is, again, as I said, are tools that developers are creating. Spark packages. You can visit there, you can add and contribute code. A lot of tutorials are there, a lot of notebooks are there that give you at least examples of things to do. And if you need to post anything in the ecosystem of Spark, they actually created, I think it's called Spark Hub or something, that you post things and they actually promote that as well. So this is one notion that you need to take into account. How many of you are creating your own data stores, database writers? Nobody? Awesome. So if you would like to create some kind of connector to your new and awesome database that does, I don't know what, create unicorns, then basically we'll put that in Spark packages. Spark SQL. Again, we don't want to work with bits and bytes. We want to work with higher level APIs and convenient ones. And most of the analysts and people that work with data science know SQL. So they've created Spark SQL as a language. And I think Avi will talk a bit about it as well, right? With the word. OK, awesome. OK, awesome. So to create SQL, what do we need? Tables. Super correct. OK, how many of you had worked with pandas in Python? Awesome. What does pandas do? It creates data frames. OK, it creates some kind of structure and utility functions on top of structured data in a matter of tables. So, of course, they copy good things. We as developers need to know copy and paste really well. So because of that, they created some kind of model that sets in mind really well about that. So they created data frames. You have data frames as well in R. And the main issue of data frames is taking the unstructured data, giving it structure and names a lot of times, for the optimizer of Spark SQL to actually know it as a table. And then he can do a lot of optimizations on top of the code and actually query relevant columns and not read the whole row, etc. So it's really important to know that data frames, I think it came in Spark 1.3, if I remember correctly. And then they actually introduced Spark SQL because now I can actually query the data as if it was a table. So it's still on the bare bones the RDD API. So we get all of the benefits of RDDs, but we take that as if it was a table. And even without Spark SQL, we can query relevant columns and not parse some kind of line and then put it in some kind of POJO or POPO in Python. POJO, plain old Java object, okay? And POPO, the same thing for Python. And it's similar to tables in relational databases. It has some kind of schema that I can query, and data frames can actually read a JSON format and then get the schema out of the JSON without me defining anything, which is pretty awesome. And you can see the Spark SQL programming guide on top of it.
So basically it has, in the world of front-end development, it has some similarity to TypeScript versus JavaScript, right?
Yes.
Structure for your data.
And I think the best example would be maybe GraphQL, which resides on,
API.
yeah, something like it. But again, I can't like correlate that in 100%. It gives you more of, let's say, it's a translator from SQL to actually running things distributed across like a lot of nodes in the RDD API. Okay, so again, we need to solve another problem. How many of you know streaming data, like streaming use cases of applications?
I'm working at Flutter. We are basically giving decisions based on transactions that some online merchants send to us in less than 1 second, using Storm to get those transactions, getting those transactions via web API and streaming them into our system with Storm, and that's it.
Storm is a framework for distributed streaming, okay, and per event processing, which is really, really important. And again, Spark Streaming is another like streaming framework, but it's more in the notion of micro batches, and I will show how it looks like. We have data inputs in which it accumulates portions of data according to slices of time. So I need to define Spark Streaming the interval of time that I'm like accumulating data upon, and then Spark Streaming takes all of the chunks of data and processes them as micro batches, which is a bit different than Storm, which actually handles every event when it actually arrives. It introduces a different set of problems. We can take these problems as processing the events only once, exactly once, or at least once. And I won't go into depth in that, but every framework of streaming handles all of these things a bit differently, and sometimes we need to even in the application layer take that in account and save that inside of some kind of data store to deduplicate the data, because I don't want to, like, if something failed and I take that event and rerun it, I don't want to have duplicate data on top of like my production database afterwards. So it analyzes all of the micro batches. Again, Spark gets that, and there is a data output of, I don't know, saving it into some kind of like data store, or maybe outputting it into the screen. So we're handling micro batches every specific second. The recommendation of the lowest time to actually process data is half a second. Okay, so like 500 milliseconds is the minimum. Usually you won't go there, because if you don't have something that runs for 500 milliseconds, you will get a lag on your data, and you probably don't want to go there. So you usually do that in a matter of actual like 10 seconds. These are the most of the use cases, or even sometimes minutes. It really depends on the amount of data, because there are some companies that can accumulate like gigabytes of data in a matter of seconds. So it really, really depends on the use case that you're using Spark Streaming. MLlib, machine learning library, really developed. A lot of people contribute to it. In the Hadoop ecosystem, we had, I really forget the name or the pronunciation, Mahout or Mahout, I don't know exactly how to, Mahout. So it was in the notion of Hadoop. Everybody practically ditched it and started working with MLlib when they started working a lot with Spark. We have GraphX for distributed graph compute. Most of the times, user will read all of the data, store that in memory in some kind of graph structure, distributed across nodes, and run usually simple things across like graph analytics on top of it, and then save it in some kind of graph data store afterwards. This is the notion of higher level APIs. For convenience, we have all of the notion of notebooks. How many of you know Jupyter Notebooks? Awesome. Great tool, right? Great visualizations, especially if we're working with Python. So we have different kind of notebooks in Spark. Some of them are more developed. Some of them were less developed and now are more developed nowadays. And you can use a lot of them according to what's needed. So you have basically Zeppelin, which is an open source project written in, I don't know what, I don't remember. But again, you can write all, it's a notebook, it's like Excel on steroids, I call that. And you can run all of the cells and from cell to cell change the languages. So basically, I can read with utility functions that I have in Scala, like in my project, in one cell, then transform it into a data frame, and the next cell will run in Spark SQL, and afterwards run a snippet of code in Python because my saving the data is written in Python in the next cell. So it's pretty awesome. There is another Zeppelin demo that you can see. I'll send the decks afterwards if you'd like, so they can actually run all of these things. No problem. And again, Zeppelin is a pretty cool use case, and IPython notebooks which you know as Jupyter notebooks. They incorporate PySpark as well. It's pretty convenient to run them, and I think Avi, you will show an example of notebooks, right?
Yeah.
Okay, awesome. Conclusions. If you've got a choice, again, Uri's first question: when you will use Spark or why? Or I think you asked Itai. Okay, Itai's first question. If you've got a choice, try avoiding distributed data stores as much as possible, because it's a fun, shiny tool, okay, but still it gives a lot of complication to running infrastructure, running production workloads. When you're starting to scale over like 100 gigabytes, terabytes, weird things happen, really. Okay, you have weird exceptions, especially in Python, specifically if you're working with PySpark. Reading all of the exceptions are not trivial at all. And if you can avoid that and put in a really hard, really strong server, do that. But if you know that you will be hitting scale sometime and you were to start working with some kind of distributed data compute framework and you want to scale linearly, which is like the dream of all of the programmers, I just put in more servers and magic happens. Nothing is magic. Spark is a great framework for distributed collections, fully functional API, and can also perform imperative programming like regular batch scripts that you can run. And again, with all of that compute power comes a lot of complexity and operational overhead. So how many of you have DevOps people? You need them, okay? You really, really need them. Most of the time spent actually is when you want to manage the cluster and everything. And because of that, if you're using a cloud service provider, please, for the beginning at least, start using the managed services. Okay, you don't want to handle the infrastructure of Spark and start learning Spark together. It's bad, trust me. And again, you need to start thinking of controlling the distribution of the workload according to partitions. How many of you are Java programmers? .NET maybe or something, not Python specifically, and not JavaScript, because when you're working with threads, this is like your distribution model, and you need to forget about threads. The analogy to threads are partitions, because all of the compute is starting to distribute across your partitions. Okay, so start thinking single-threaded. So Node.js is a good example for that. Start thinking single-threaded, and everything runs on one partition. This is the file that you're working on top of. And multiply it by the amount of servers that you have. And no more threads. Again, after talking, I think, pretty fast, but I slowed it down a bit. Do you have any questions about that?
אפשר גם לשאול בעברית.
כן, אין לי בעיה, אני יכול לזרום גם בעברית.
מה, אתה מדבר עברית?
Don't tell them. כן, איתי.
מתי אתה משתמש בהדופ ומתי בספארק?
Okay, so when will you use Hadoop and when you will use Spark? First of all, if you would compare some workload, it doesn't really matter. One batch operation that I will start off. Everything in the world of Spark starts off from reading data from somewhere, okay? If not, it's pretty useless to actually use that. So we read data into memory, do some kind of transformations or actions on top of it, and then put the data somewhere. Because if we don't have this process or workflow, it's pretty useless to use this, okay? So if we have something that does only one transformation, I won't say that in 100% of use cases, but mostly it will be the same. Okay, because you read something into memory, it doesn't matter if it's like the MapReduce regular Hadoop ecosystem thing or Spark, and then you write it. So it will be the same. But if you need to do multiple transformations, Hadoop will always thrash the disk, and like in the next phase, will read that from disk. So because of that, they say the Spark is like 10x or 100x faster than Hadoop. And sometimes you will use the combination of the Hadoop ecosystem with Spark, because it runs together, right? You will use HDFS as a distributed data store, and Spark is the compute framework. So it's basically using both of them, right? But you probably meant MapReduce. Usually you won't use that nowadays. But again, like 2 or 3 years ago, I heard that like in the matter of petabytes, then Spark starts being flaky. I think that today it improved a lot, but then I think eBay, a friend of mine, told me that he's using Spark for some use cases, but the old MapReduce that runs like for years still works in petascale. Most of us won't get there. Okay, we're not Google. Yet, yes. שאלות. גם דברים כאילו, if you have like, this is really introductionary, okay? If you have like complex things, I can talk about it as well, problems in your infrastructure, and if you'd like, you can come afterwards and talk to me as well. You're more than welcome. And another thing, if you need anything afterwards, just ping me. I think I'm really available on most of the social media, and you can ask questions and come to the meetups as well. To Dev.IL, to Big Things, to GDG Cloud. Learn new things, because even if you don't know anything and you're not using that on the day-to-day basis, sometimes you can take that and project that to the things that you are doing, even in front-end development. And it's awesome, because I really learn from all of the worlds, like when I'm visiting different kind of technology meetups. Thank you very, very much.